yesterday we focused a lot on Riemann sums, area under the curve, and making that first introduction to integration. Today we're going to take it one step further. We're going to talk about the fundamental theorem of calc. Fundamental theorem of calc is the most basic understanding of integration. It tells us that there is a connection between differentiation and integration. It says that if f is a continuous function on an interval, then the derivative of the integral is equal to the original. So again, it shows that differentiation and integration are inverse operations of each other. So if I take the integral and then I differentiate it, I will get back to the original function. If f is a continuous function on an interval, capital F of x will equal the integral of a to x of f of t dt. It is called the antiderivative. It is what comes before a derivative. And then we have our rule that says if you integrate a to b of f of x dx, then you get capital F of b minus capital F of a. So we can use this to help us with values of g from a graph of f. So oftentimes on the AP exam, they're going to give you a graph of a function. In this case, our function is f. And they're going to give you a relationship between g and f. So g is equal to the integral of f of t starting at -1 and going to x. So if you are looking for g of 3, then you are taking the integral from -1 to -3 of f of t dt. Now, the bounds are relatively backwards in this case. So you need to take into account, so if you recall the direction of integration, and that's kind of what I'm putting here, and the location of the graph, this result is going to affect your integral. So from -1 to -3, we're working backwards. So area under that curve is really going to be a triangle. The triangle area is negative, but you went backwards. So your final answer is positive. You would have had a negative area, but you have a negative for the integral, thus a positive answer. if your upper and lower bound are identical, then the area under your curve is 0. So g of -1 is 0. G of 1 goes from -1 to 1. So it's going to be the next big triangle. Triangle 1 unit tall. And then for 3, you have 2 choices. You can make it that your initial value is g of 1, and then you can integrate from 1 to 3. Or if you do g of 3 and you take the initial starting point of -1, then now when we find this area under the curve, we have to go from -1 to 3 and change my shape to a trapezoid. Or again, you include that triangle and then find the trapezoid of the remaining. Either way, you'll get 5. If the initial starting point was something other than -1, which was at 0, then you could have had an initial condition. So they could have made the integral from 1 to x, but they would have to have told you that g of 1 was 2. And then you would need to use that 2 in your problem. Much like we used the 2 here and then found the new height. It says, using the points from the previous slide, graph g of x. So we're going to start with g of -3, which is at 1. So we're going to plot the point -3, 1. So taking into account the relationship between them, if g of x is equal to the integral of f of t, that's kind of like saying g of x is equal to capital F of x. which means that g prime of x is equal to f of t. So when we're talking about these concavities, these increasing, these decreasing, we don't really know like if that's solid, linear, etc., without taking into account the table here and that relationship there. So I know they're going to be connected, but in order to get all of my true answers, g of x is increasing if g prime is related to f when f prime is positive. And that holds true to my graph points, correct? It's decreasing when the graph is negative. G will be concave up if my derivative is increasing. What would be a good calculus-based justification? So again, if I were to write that in a sentence, I would say that the graph of g of x is concave up when f of t is increasing. Therefore, -2 to 1. You have to talk about each graph with respect to what you have. We know that it is concave up on that graph because it is increasing. It is concave down when it is decreasing. We don't include that 1 to 2 because the graph is flatlined. The derivative of a flatline graph is 0. 0 is not going to be concave up or concave down. It's going to be 0. What is the relationship between f and g? So that relationship is what I put here. G prime of x is equal to f of t, f of t. Make sense? Roughly something like that. Yes. Okay, given that f is twice differentiable, thus differentiability implies continuity for both f and f prime. What is the value of 0 to 6 of f prime x dx? So you are integrating, therefore this is equal to the original at 6 and 0. So if you integrate the derivative, it's equal to the original at those bounds. We have a couple rules that we can apply. So again, this comes into play that reverse interval rule is what we saw at the beginning where the bounds were flipped. So in order to make the bounds normal, you take the negative. So if you are given a graph with areas on that graph, what you can do is use that. So -2 to 0 plus 0 to 3 -1 to 3 3f of x would be like saying 3 times -2 minus 2 times 5. You can think of them as separate. The constant gets multiplied and makes that bigger. If your bounds don't match what you are given, then you rewrite your integrals to make them match. So if I need to go -3 to 5, but I know -3 to 1, then I'm simply going to add 1 to 5 to make my bounds -3 to 5. So all I'm going to do is add that 8 and 6 together to get 14. So that differentiability aspect tells me that this is continuous. I am also given in this case an initial condition because we are told that f of 4 is equal to 3 and I'm given f prime. So that f of 4 equal to 3 is my initial condition. That is the starting point I need to use when finding f of 0 and f of 5. So f of 0 and f of 5 are FTC problems in the sense that f of 0 is going to equal f of 4 plus whatever my integral is. So you're taking that idea in the case of this problem, and this is like saying, okay, I'm going from 0 to 4 of f prime of x dx to, which is equal to f of 4 minus f of 0. That's that problem we just set up, but in the table. So now, if I want to know f of 0, then I need to flip f of 0 and my integral, so that f of 4 minus the integral from 0 to 4 of f prime t of x dx. Where the integral represents the area under the curve, so the area under the curve from 0 to 4 is negative, and it's a semicircle. So it's a semicircle of radius 2, so 2 squared is 4. 4 divided by 2 is 2. Then you have minus minus, so we get 3 plus 5. F of 5 is just going to be taking the values here and manipulating them again so that I have 4 to 5 now, which means this is f of 5 minus f of 4. So to solve for f of 5, it's different than f of 0, because now we're going forwards. So f of 5 is going to equal, we're adding f of 4 to the other side, f of 4 plus the integral from 4 to 5. They purposely leave out the point at 5 because they want you to take into account the slope from 4 to 6 is 1. So you know that it's at 1. Because if you go over 2 and up 2, then your slope is 1. On the 2022 AP exam, this question was worth 3 points. You got 1 point for having either integral. So you got a point if you wrote this or that. Your second 2 points came from the correct answers here. So again, part A on the 2022 FRQ was worth 3 points. Part B, find the x-coordinate of all points of inflection for the graph of f from 0 to 7. Justify your answer. So again, taking into account that this graph represents f prime. So we're living in this column, but I'm trying to identify this. So a point of inflection on f will be at an extrema of f prime. So I'm looking at this graph and I am looking for extrema. So for part B, you would say that the graph of f has a point of inflection at x equals 2 because f prime, which is the graph we're given, how do you get a point of inflection? You need to change concavity, which means it needs to go from increasing to decreasing, as well as containing that extrema. So you'd say that the graph of f has a point of inflection x equals 2 because f prime changes from decreasing to increasing and f prime of 2 equals 0. You could say that you have a second point of inflection at x equals 6, but your reasoning is different. The graph of f has a point of inflection, so assume I reroute all of that, at x equals 6, because f prime changes increase to decrease, and f prime of 6 does not exist, because that is a point of, well, a double prime, of 6. You could earn 1 point if you only had 1 point of inflection. So if you only had x equals 2 because you didn't think 6 was 1, you could have earned one of the 2 points. To earn your point, you must have your justification with respect to f prime. So how I used f prime to talk about it, if you do not talk about f prime having that extrema or having a change from decrease to increase, you cannot earn those points. You could not earn a second point if you called it or the function or the derivative. So if you said the derivative, you did not earn your second point. Okay, part C. Let g be the function defined by g of x equals f of x minus x. On what intervals, if any, is g decreasing for 0 to 7? So again, g of x equals f of x minus x. So in order to know if g of x is decreasing, I need to know what's happening on g prime of x. So g prime is going to be equal to f prime minus 1. So is that -1 going to change anything with respect to g being decreasing? So g will be decreasing if f prime is negative. So what that does is that would shift this graph down 1. So essentially, it makes that your new x-axis. So instead of looking for a negative below the x-axis, we're looking for the negatives below y equals 1. So g prime will be decreasing from 0 to 5. So you got 1 point if you labeled and listed this. And a second point came from your interval. But to earn the full second point with the interval, you had to put a reason. So that reason is kind of like what I was verbally saying. So the reason or the justification is that because G prime shifts f prime of x down 1, then it will be where f prime of x is less than or equal to 1. You actually could have your justification with respect to f or g. So they also had on there that g prime of x is decreasing or sorry, g of x is less than or equal to 0. They also would accept that as a justification. And then part D, for the function g defined in letter C, find the absolute min on the interval 0 to 7. So now your graph of g is really the graph of f prime, as if the line y equals 1 is your x-axis.